So we're getting to the end now of the properties of Fourier transforms, but there's one here which I think has to be my favorite, certainly the one that I've used the most in my career as a physicist, and that is what the Fourier transform does to a derivative. Fourier transforms magically simplify derivatives. So for a derivative f dash of t, which is the time derivative, if this is the Fourier transform defined like this, so that we have some function f of t transforms to this function capital F of omega, then the Fourier transform of its derivative is equal to I omega times the Fourier transform. So in other words, if you have a function which is differentiated here, you take the Fourier transform, then the transform has no derivative in it. Instead, the derivative turns into a multiplication by I omega out the front. And it's actually not so bad to prove. So let's start with the function f of t. We're going to write that as its Fourier transform inverse transformed. So this is the Fourier transform of f of t, inverse transform it must be equal to itself. We're going to expand this inverse Fourier transform as the integral divided by 2 pi, and then it's integrated by multiplying by e to the I omega t d omega. So this is the inverse transform of capital F of omega. Now we take the derivative. So the derivative of f of t is f dash t. We don't know the function, so it's just the dashed. We can take the derivative inside this integral though, because there's only one part that depends on time, and that is this e to the I omega t. When we take the derivative of e to the I omega t, that gives us this factor of I omega here. So then we can just compactify the inverse transform again, because we've still got all the same inverse transform machinery at the front here with the 1 and 2 pi and negative into infinity to infinity, and the same thing at the back. So we get the inverse transform of I omega times capital F of omega. If we now take the Fourier transform of all of this equation, the Fourier transform of this derivative must be equal to I omega times capital F of omega. So we've proved our derivative theorem. More generally, you could do the same sort of proof for any higher order derivative. Every time you differentiate, you get another factor of I omega out the front, and they all just multiply together. Now, this property can be used for simplifying differential equations, and this is where it can be super useful, and where I've found it super useful over the years. Let's have an example of this equation here. It's an equation for a damped driven harmonic oscillator. We have second and first order derivatives. If we take the Fourier transforms of both sides of this equation, then the second order derivative gives us two factors of I omega. So I omega to the power of 2, that gives us a negative omega squared. The single derivative here gives us a factor of I omega. The other terms have no derivatives, so it's just the Fourier transform of x gives us capital X of omega. Fourier transform of f gives us capital F of omega. And then these parts here that have the derivative, well, we get the same x of omega. So this is x of omega, x of omega, x of omega, and the only thing the derivatives have done is given us factors of I omega out the front. So the differentiation has disappeared, and we've turned a differential equation into a linear equation. And we can solve it. We can rearrange for x of omega. So this is the solution for x in frequency space as a function of the force in frequency space, with this denominator here, which may be familiar if you remember material from looking at damped driven oscillators. Now we'll come back to solving differential equations and treating differential equations using the Fourier transform later on in this course. This is just a little taster for now.